Good day, dear students. This is Dr. David Pokrajak. I will lecture about the data structures for disjoint sets. So let me briefly review what we did last time when we talked about disjoint sets. Basically, what are disjoint sets? Consider the sets S1, S2, Sk. These sets are called disjoint if the sets are like this. In other words, what we can see is that none of the sets intersect with each other. In other words, what we can say is that for any two sets I and j, the intersection, whenever Si is Sj, yeah, in other words, actually better to say problems with technology. The Si intersection with Sj is equal 0 whenever I is different from j. If this condition is satisfied, then the two sets are pairwise disjoint. And basically what we can assume and what we assume when we are working with disjoint sets is that the union of all sets is equal to the universal set. In other words, each element must be element of precisely one set S1, S2, and so on. For disjoint sets, we define the following operations. The first one is to create a set consisting of one element, and the operation is called make set. We create the set S consisting of element X. We can think about this operation as constructor. We construct a set. Another operation is find set. Argument is X. Basically, what we find a set which contains a given element X. And the third operation is this. What this operation does, it finds a set Sx such that element X is from the set Sx, then finds set Xy such that Sy contains an element Y, and finally creates a set S, which is the union of the sets Sx and Sy, Sx and Sy. What we also discussed is one of the applications of this, which is basically to find connected components. What does it really mean? As we discussed, we basically have certain graph. For instance, in this case, we have elements A, B, C, D, E, and F. And as we can see, there are three disjoint subsets, S1, S2, and S3, such that if the vertices are from different sets, the vertices are not connected to each other. And if the vertices are from the same set, then they must be connected to each other. And what we were discussing is the algorithm how to find the sets representing these connected components. And the algorithm was this. So basically I have a G. G is a graph. And then we do the following. What we first do, we create sets such that each vertex of a graph is in a separate set. What we do next, basically we go through the edges of a graph. And whenever two vertices are connected by an edge, we basically find the sets containing these two vertices and basically merge these two sets together. In other words, we do this. So this is an algorithm which basically finds the connected components. In order for this algorithm to work, obviously we need to have efficient implementations of make set, find set, and union. What we, I believe, started last time is a linked list representation of disjoint sets. So first, what is a linked list? Let's assume that there is a set S containing elements X, Y, and Z. The idea is to basically create a linked list of elements X, Y, and Z. So when we create this linked list, of course I will somehow put them in any order and create a linked list. Of course, in linked list, each element of a linked list has next pointer, right? So the next element to X will be Y, the next element to Y will be Z. And of course there is no element after Z, so the next pointer of Z would point to nowhere. It will be a nil pointer. So this would be a simple linked list. And I basically can have a head pointer to a linked list. And the head pointer of a linked list, of course, would point to the first element of the linked list. In this representation, I would also like to have a tail pointer. So the tail pointer would point to the last element of the linked list. In addition to this, I would introduce another pointer in each element of the linked list. And such a pointer would point to the head. So let's show these pointers too. So these pointers point to the head of the linked list. And basically now we can put head and tail together, and this will represent my disjoint set S. So what would be the obvious operations of this? First, to create the set. How we will create the set? To create a set, I need to basically create a linked list. So if I am given an element X, here is what I need to do. 1, I need to allocate space for my element x. It would point to nowhere. There will be a nil pointer. And then I would need to have head pointer to this element. I will need to have a tail pointer. A tail pointer would point to the same element because that element is at the same time the first and the last element of the list. And in addition, simply for consistency, that element would point back to a head. So literally these will be the operations I would need to perform. Allocate space, head and tail points to that space, and we need to point back to the tail. What is the complexity of this? Obviously I need a total of several operations, 3 or 4. It would be 4 if we consider making head and tail separate operations. So the number of operations is constant, and it will be, of course, because it's constant, it's order of 1. So far so good. I have a efficient make set. How about find set? Let's assume that I'm given a linked list representing my set. So here is my linked list. Here is the linked list. Somewhere in the linked list there is an element x. From each element I point back to the head. So how I will find the representative of this set? First, we would assume that we know where is x. First step, follow a back pointer. Following the back pointer, we will go to the head. Second step, for head, following the head pointer, I would find the first element of the linked list. Let's call it y. Basically y, the first element of the linked list, would be considered the representative of the disjoint set. Again, we have a constant number of operations, which is order of 1. So far, so good. Now, remaining problem is how to find union of two sets. So now let's assume that we have the first set, Sx, which somewhere contains x. And Sy, which somewhere contains y. Of course, don't forget the back pointers, as well as the tail pointer. Now the question is how we will do the union of these two sets. A logical way would be choose one of these two sets and on that set append another set. Right. So this is precisely what we will do. So say that we append sy to sx. How I will append sy to sx? First, I would start from x. As we did in find set, I will start from x, and I will find sx, the head of sx. Similarly, I will start from y, using the back pointer, and I will find sy. I had two operations at this moment. So now what? I need to append sy to sx, which means that I would need to find the last element of sx. So let me just summarize what we did up to now. This is what we did up to now. Then the next step, I need to find the tail of sx. Basically find the last element of sx using the tail pointer. So after the operation 3, I found the last element. Okay, now what we are going to do? I need to continue from the last element of sx to the first element of sy. So I didn't show the first element, the representative of sy, so that here would be the first element, the representative of sy. What I need to do is to now connect, instead of this nil pointer, here was the nil pointer, right? Instead of having a nil pointer, the last element here, I would need to point this element to the first element of the second linked list. In other words, I would need to establish the following link. Now, as we can see, the first element of the second linked list would point to this last element of the first linked list would point to the second element of the second linked list. Wonderful. However, we still have some problems. Each element of the second linked list has a back pointer pointing to the head of the second linked list. I need to redirect each pointer, each back pointer, of the second linked list to point to the head of the first linked list. In other words, I need to re-establish the following connections. How many connections should be removed? The total number of connections that should be removed is equal to the number of elements in the second linked list. In other words, back pointers from the second linked list now point to the head of the first linked list. What is the total number of operations? Obviously, for the operations 1 to 4, we have a constant number of operations. When we reconnect, which means the phase 5, the number of operations is exactly equal to the number of elements of SY. So the number of operations is equal to the size of SY. Just to recall, this means size. So obviously we have two choices. Either we will append Sx to Sy, or as we did here, we would append Sy to Sx. What is better? It is better to append shorter set to a larger set. In other words, what I just said, if Sy has less elements than Sx, we would append Sy to Sx, as we demonstrated above. Otherwise, we will append Sx to Sy. What would be the complexity of all of this? I mean, we now know the complexity of each particular operation, but obviously the total complexity would depend not only on the number of operations, it will also depend on the number of elements, right? So what can be proven? Let's assume there are n elements and there are a total of m operations. Does it mean that there are n elements? For each element we would need to make a set. So basically there are n make set operations. Let's assume that the total number of operations is m. So we perform a sequence of operations which may contain make set or union or fine set. And M is the total number of operations. There is a theorem, which I will not prove here, but I believe the proof should be in the textbook. And the theorem says that the complexity is of M operations, of which N make set operations, the complexity of all of this is this is the complexity. So the question is, can we do better? And the answer is yes, we can. So how we will do better? Should be obvious that we need to have some other representation of disjoint sets. We tried with linked lists. Yes, it did work, but we claim it can be done better. So maybe we shall choose another representation of a linked list. Sorry, another representation of disjoint sets. And obviously I don't want to use linked list. I want to use something else. What else? Ideas? Do you have any ideas maybe? Yes. I wish I could talk to you and look at your eyes, but unfortunately this is a one-way technology. So another way we can represent disjoint set is using trees. So let's look at two disjoint sets. For instance, one set can be S1, consisting of elements B, C, E, and H. Don't ask me why I chose these letters. And S2, consisting of D, F, and G. If I use trees, I may represent these two disjoint sets this way. So basically, I use trees to represent the disjoint sets, and a node points to only to a parent. There are no any other strange pointers as existed before for the linked list representation. How we will perform operations in this case? First and obvious, make set consisting element X. I need to create a tree with X as the only element. So create a tree with X on its root. Simple and obvious order of one, right? fine set. So let's assume we have a tree. Tree, right? And somewhere in tree there is an element x. How I will find a set? What does it mean to find a set? It means find the representative of a set. Here the representative of a set is a root node. So let's assume that I know where is my x. I will basically go up and up and up until I reach the root node of a tree. And the root node of a tree will be my representative. What is the complexity here? The complexity here depends on the level of my node x. What is the consequence? I would try to have a level of a particular node x as small as possible, which means I'm trying to somehow discourage these balanced trees. The third operation, union. Let's assume I have two trees, right? The first consists of now well-known nodes C, H, E, and B. And the second one consisting of nodes F, B, and G. As the first step, of course, I would find the representatives. Here are two of my representatives. And then I would need to basically merge these two sets. How I can merge these two sets? Either I will connect C to F or F to C. In other words, I have two possibilities. The first one is this. So I have two trees. And now I connect node C to node F. In other words, I connect tree corresponding to set S1 to a tree corresponding to a set S2. And the representative of the second set, which is F, becomes a representative of the union of sets S1 and S2. Another possibility is to connect S2 to S1. So this is my S1, this is my S2, and now I will connect the representative of S2 to the representative of S1. And I will get something like this. Which way I would choose? Generally, I would choose a way which leads to more balanced tree. But apparently I need to formalize these heuristics somehow. So what are the heuristics? Remember, and it's not very difficult to remember, that when we represented disjoint sets using linked lists, I basically check the number of elements, in other words, the length of each linked list, and then I merge a shorter linked list to a larger linked list. So it makes sense to have similar heuristics in this case. What we will do, we will calculate a rank of a tree. Actually, better to say we'll maintain rank as a property of a tree. And then we will merge a tree with a smaller rank to a tree with a larger rank. So these two together comprise a heuristics which is called union by rank. And again, it consists of two parts. Determine what is the rank of each tree and then merge the one with smaller rank to a tree with a larger rank. Again, to point out, the heuristics for the linked list representation is similar. There, I merge a linked list with smaller rank to a linked list with a larger rank. And the rank could be defined as the number of elements in the linked list. Here, as we will see shortly, we would need to devise another way to determine a rank. So this is one heuristics. However, we would adopt another heuristics too. Another heuristic basically helps to balance a tree differently. So that heuristic is called path compression. And we could explain that heuristics as flatten the tree while performing find operation. So let's do the example for path compression. Let's assume here is our tree. R denotes root. Then we have nodes B, A, and somewhere there is node X. So normally what I would do, I would start from node X and go until I reach the root. and then the root will be the representative of my disjoint set. During the paired compression, each node from X to the root is going to be reconnected directly to a root if it is not already connected there. So basically this is what we are going to do. Here is my root. Here is my node X. On my node, on my way from X to root, from X I will reach node A. From A I will reach node B. And then each of them, if not already connected, B is already connected to the root, right? Other nodes, since they are not already connected, will be reconnected to the root. As we can see, this drastically flattens the tree. Basically, in original tree, X was 3 steps from the root, and now any of these nodes would be exactly 1 step from the root. So this is the paired compression. And of course, there are some technicalities how to do all of that, because obviously we would need to know where is my root. So first I would need to find the root, and then to go back from X, and then to reassign each of its parent, grandparent, and so on. I shall assign to them the pointer to point to R. Let's now look in more details into union by rank. So we are now looking at the union by rank. What I've already told you is that we need to keep the rank of the tree. In fact, we will not keep the rank only of a tree. We will keep a rank of each node of the tree. So, and as I said, when we do the union of 2 trees, what we will do, I will check the ranks. Basically, R1 and R2 are the roots of S1 and S2 correspondingly. I check the rank of a root R1 and R2. If the rank of R1 is smaller than R2, then I will merge the first set to the second set, the first tree to the second tree. Otherwise, I will do the opposite. Why rank? Logical question, why rank? Again, let's go back to the previous example of 2 trees that need to be merged. Let the first tree be like this. And the second tree be like this. If I merge the second to the first, the result will be like this. This is if I merge the second tree to the first tree, the second tree to the first tree. If I do the opposite, this is what I will get. And this will be the result of merging the first tree to the second tree. So in the second case, we can see that the total depth would increase in comparison to the first case. So it's better to merge a short tree to a large tree than the opposites. Basically, I would like to have a rank somehow measuring the total depth of the tree. Easy, right? But we still did not define the rank. So in order to see how we will really calculate the rank, we need to see how we will implement in a little bit more details these trees. So each node has, now we know that each node has a rank. That's one thing. And then another thing is each node has a pointer, parent pointer. Well, each node has a parent pointer, but can we say that each node has a parent? No, we can't, because the root does not have a parent. So in that case, I can point the parent pointer of a root to itself. How now make set would look like? So I want to create a set consisting of element x. Initially x is a root node, so a parent of a root doesn't exist. A parent pointer points to itself. There are no nodes below a root, right? So there are no nodes, and the depth below that node is 0, because there are no nodes below. Due to that, I can say that the rank of a node is equal to 0. And we can see that rank represents depth below node. If a node is if a node is root, this depth is 0, right? Before I consider how I will do union, I will just write find set. So I'm giving an element x. So I'm checking whether x is a root. If x were a root, then the parent pointer would point to x. So this if would not be satisfied. Otherwise, x is not root, so we need to go one step up, recursively call. So basically, this is what I'm doing. What is this doing, really? There are two things that are done here. First, this calls recursively from a parent, which it should. So if I did not reach a root node, I would need to go to a parent. And after basically find set returns, I connect parent pointer to the root. Why I'm doing this? Remember path compression. In path compression, each node on a path is going to ultimately be connected to a root. So this is what we are basically doing. We are at x. If we did not reach the root node, what I will do, I will apply the same procedure recursively to the parent. And once I find the root node, I would reconnect my node x to the root node. This is what this find set procedure does. Of course, what I forgot, but I will not. So if we did not reach the root node yet, we will reapply procedure recursively and reconnect. Otherwise, if this if is not true, I am at the root. So since I'm at the root, I basically can return the pointer to that root. And this is exactly the pointer to the root, because for a root parent pointer points to itself. So this would be find set. Very nice and elegant. And what is also very elegant, that we were also able to incorporate here the path compression by reassigning the pointer. We still don't know how to make the union, how to merge two sets. To make the union, I need auxiliary procedure, which is called link xy. So basically what this procedure does, we assume that X and Y are roots of two trees. The heuristic says, find a tree with a smaller rank and merge to a tree with a larger rank. So say we are doing this. We are comparing the ranks of X and Y. If this if is true, this means rank of a tree rooted at Y is smaller than rank of another tree. If it is true, the heuristic tells us to merge a tree which is rooted at Y to a tree which is rooted at X. How to do that? Basically, that means that the parent of a root Y now needs to point to another root. Simple, isn't it? Oppositely, obviously, rank of Y will be larger or equal rank of X. In that case, we would need to merge tree rooted X to the tree rooted at Y. In order to do that, the parent pointer of X, which is the root of the first tree, would need to point to the root of the second tree. Observe that this is exactly opposite to this one. And there is one more bookkeeping step. What does this tell us? Let's assume that this if condition is satisfied. Let's assume that this if condition is satisfied. I will connect another level below Y, because now this tree is connected to this tree. In that case, the number of nodes below Y to the leaves will increase by 1. In other words, this would be the illustration of that case. This will be my S2, this will be my Y, this will be my S1, this will be my X. In this case, Y dot rank is equal 1 and X dot rank is equal 1. I would merge the first to the second tree, and the result would be like this. So I merge the first tree to the second tree. And now the number of nodes below y increases by 1, because now y is connected to x. And in order to follow that, I would need to increase the rank of y. So this will be my procedure to essentially connect two trees rooted x and y. In order to really do union operation, what union operation does? Union operation first needs to find representative of a tree containing x. It needs to find for that. So union operation finds the representative of the first set, finds the representative of the second set, and then basically this would be the root of the first set, the root of the second set, and then it needs to link the roots of the first set and the second set. And again, in order to do union of two sets containing x and y, I will need to find the root of the first one, the root of the second one, then to link these two roots. This would be the union operation. Whew. It can be proven, but we will not prove it here, that upper bound of the longest path from x to any of the children. There is another theorem which can be proven, which has two parts. If we use only union by rank, that means that we do not do the path compression, right? So we're just going from one to another node, and we do not really change the connections. What will be the part of your homework is to modify find set when path compression is not used. So if we only use union by rank, there are a total of m operations. Of which there are n make set operations. It can be shown that the time complexity for this set of m operations is m log n. However, if we combine both heuristics, the complexity becomes much different. So the question was what is alpha of n? Alpha of n is defined in your textbook, but what you really need to know is that alpha of n is smaller or equal than 4 for, look at this number, so even if n is 16 to the 512th power, alpha of n is smaller or equal to 4. So what is 16 to 512? This is 2 to the 4 to 512, which is, these numbers are killers. 2 to 248. 2 to the 248 is larger than 2 to 20 times 100, right? Because this is smaller than this. Which is equal to the 20th, 100. 2 to the 20th is 1,048,000 whatsoever. So it is larger than 1 million to the 100, which is 10 to the 600. So, as long as we make, what is n? N is the number of make set operations. As long as number of make set operations is less than 10 to 600, which is, I believe, called centillion, which is still a large number, alpha of n is smaller or equal to 4. Well, the number of atoms in the universe is probably the order of 10 to the 80. So for any realistic purposes, alpha of n is basically a constant. As a consequence, for all practical purposes, this theoretical complexity is in fact order of n, because alpha of n is for all practical purposes constant. So what this tells us, if I have total of m disjoint set operations, the time to perform m disjoint set operations is order of n. So the average complexity per operation is order of 1. So the end of this long journey basically tells us the following. It was really a long journey, right? This would be the complexity if we use linked list. So if we use linked list, it is order of n plus n log n, right? If we smartly these, we are basically at order of n. Now really doesn't depend, practically doesn't depend on the number of the elements in the disjoint sets. And the complexity of m operations is order of n, which means that basically we can on average perform one operation per constant factor. I think this is a very good illustration how using smart data structures can make work with the data much more efficient. There is one more thing which is totally different from what we did up to now. Up to now we were doing the disjoint sets, and there is one more thing which needs to be covered in this lecture, which is representation of graphs. So when we talk about graphs, we are talking about vertices, right? We usually call vertices V1, V2, V3. We'll see what's the total number of vertices. So if V is the set of vertices, then this is the total number of vertices, right? So these are our vertices, right? We are talking about set of edges. And we can represent the set of edges what I wrote here is the following. Set of edges is in general case set of tuples, pairs, right, of vertices. This basically indicates that Vi and Vj must be in the set of edges, and this is the set of edges. Of course, if the graph is not directed, then basically the order of the elements in the pairs wouldn't matter. So there are two ways how we can represent the graphs, and depending on the application of the algorithm, we may use either one or another one. One is using a matrix. So this matrix is called adjacency matrix. Let's give an example of a graph. So this is essentially an arbitrary directed graph. Example of the graph. So who is neighbor with who? That's basically what the adjacency matrix tells us. So what are our vertices? Our vertices are A, B, C, and D. So we create a matrix which is quadratic matrix with rows and columns corresponding to the vertices. And now let's look at the graph. If A is connected to B, then element AB will be equal 1. B is connected to D, so BD element is 1. B is also connected to C. C is connected to D, and D is not connected anywhere. So this would be our adjacency matrix. The other elements will be equal 0. This is the adjacency matrix. If a graph is not directed, the matrix will be symmetric. Example of that. In fact, I can do exactly the same graph, except now this graph is not directed. As we can see now, there are no arrows. The corresponding adjacency matrix would be this. So now A is connected to B and B is connected to A. A is connected to B and B is connected to A. B is connected to C and C is connected to B. C is connected to D and D is connected to C. Did we miss anything else? B is also connected to D. B is connected to D and D is connected to B. So now this will be our obviously symmetric adjacency matrix, except I would need to add zeros where there are no connections. Finally, we can use the same representation of adjacency matrices also if I have a weighted graph. So let's give an example of a weighted graph. And I will put here also loop and return. So here are my edges, arcs in this case because it's a weighted graph, and here are my weights, say 2, 3, 4, 5, 1. The adjacency matrix would be this. So A is connected to B with weight 2. B is connected to C with weight 4. B is connected to D with weight 3. C is connected to B with weight 5. C is connected to D, I forgot to write weight, say 6. C is connected to D with weight 6. And D is connected only to itself with weight 1. So as we can see, because there is loop, now there is a diagonal element equal to 1. And again, other elements, when there is no connection, the other elements will be equal to 0. So this is basically our representation by adjacency matrix. Another representation is using adjacency list. Let's again give the same example of a graph. Basically what we do, we create a list of all the nodes that are connected to a particular node. So this will be a list of all nodes directly connected to A. And it will be only B, right? The list of all nodes connected to B will be C and D. C and D, right? And the list of all nodes connected to C will be D. What shall we be concerned here about algorithmically, right? What we shall be concerned is really about the space complexity. So what is space complexity for representation? Let's first look at the adjacency matrix. Essentially, we would like to answer to a question: how many rows, how many columns? The number of rows and columns are this. The number of vertices, right? So the size of matrix will be the square of the number of elements. This will be complexity for adjacency matrix. Again, this is space complexity. We are talking about the space, total amount of memory. So, for adjacency matrix, it's basically depending on the square of the number of vertices. How about adjacency list? We create one list for each vertex. So, the total number of lists is this. The total number of elements in all the lists, in this case, is 4, which is exactly the same as the number of edges. I have 4 edges, and I have total 4 elements in all the adjacency lists. So the total number of elements in adjacency lists would be equal to the number of edges. And I would need to keep the pointers to each adjacency list plus all the elements of the adjacency list. So the total space complexity will be exactly this. The number of elements, the number of lists, the number of vertices, right? Plus the total number of edges. So this is complexity for adjacency lists. And somebody can immediately argue, okay, having in mind only the time complexity, the space complexity, we're talking about space complexity, yeah? Having in mind the space complexity, what is best? And the answer is actually depends. If the number of edges is relatively small, when we are talking about sparse graphs, then basically the complexity of adjacency lists would be smaller. So, the sparse graph, adjacency lists have smaller spatial complexity. Why I'm mentioning this here? Because whenever, especially in this course, we need to learn that we always need to think about space and time. Okay guys, this concludes my first ever recorded lecture using this technology. And I hope you enjoy that. I hope I will learn how to turn off this stupid message cloud is full. Now I'm gonna store this and hopefully upload.